I'm James Ward from TypeSafe. I'm a developer advocate there. And today's webinar is going to be about Akka Persistence. And we have with us Patrik Nordwall, who is a member of the Akka team, one of the core engineers there. And so what we're going to be recording this session, so if you have to step away or want to send it to your peers afterwards, then you can do that. We'll send out the link to the recording once it's posted later today or tomorrow. Also, we'll be doing question and answer at the end of the webinar. So if you have any questions, there's a questions pod in the Go To webinar, and you can just enter all your questions in there, and we'll do the Q&A at the end. So as we're going through, feel free to ask your questions. If you have any problems or technical issues, feel free to enter those in the questions pod as well. So with that, I'd like to hand it over to Patrik to tell us about Akka Persistence. Patrik, you there?
Yes, I'm here, James. Thank you. Welcome to this webinar. It will be great fun to present Akka Persistence, which is a new module in Akka 2.3. So Akka Persistence is bringing two things to you, and that is helping you with recovering application state after crashes. It can be JVM crashes or it can be server crashes. In some way, the state of the actors can be recovered to the same as it was before. The second thing that it brings is a way to communicate between actors in a more reliable way than the default. It provides an optional way to send messages with at least once delivered semantics. So today I will describe how these two things fit together and how to use them in Akka Persistence. So the 2.3.0 release was shipped just a few weeks ago, and it comes with this new module. And on this slide, you see the dependency that you need to add to use Akka Persistence. As you can see from the labels there, or the artifact names, this module is marked experimental. And that's the way we always release new features in Akka. The reason for that is that we want to be able to adjust the feature based on your input. So we have some more freedom with regards to changing the APIs. Of course, we try to not change the APIs if there's no motivating reason for it, but we would like to have the possibility to do that. Also, it makes it possible for us to do binary incompatible changes in minor releases. In, for example, 2.3.1, we could potentially do a bug fix that is not binary compatible in those experimental modules. It's the same there. We always try to do it binary compatible, but it makes it possible. Another thing to note, I will show some examples in this presentation, and they will be showing Scala code. Everything I show will, of course, be possible to do with Java as well. So Akka Persistence provides excellent APIs from both Java and Scala. So first of all, I would like to send a big thank you to Martin Kresser, who has been the main developer of Akka Persistence. He has been working as a contractor for TypeSafe for about half a year now. And he has done some really amazing work, and it has been a great pleasure to work with him. So I've been working closely in the Akka team with Martin. Previously, Martin developed the event-sourced open source library, which has similar features as Akka Persistence. And of course, we have taken advantage of everything that has been learned in that project. But Akka Persistence is really a rewrite. It's a new thing. It's using the same concepts as event-sourced, and you might recognize some of them, but it's a complete rewrite, and we have iterated over this half year over a lot of new ideas and ways to do it better. I saw in the poll that several of you, I think it was 7%, that had been using event sourced previously. And in the end of the slides, I'll have a link to a migration guide that you can use to see in more detail what the differences and commonalities are. So in some way, we need to store the state so we can recover it after crashes. The traditional way of doing that is storing the structure of things. It could be in a relational database. You store things in different tables and link them together. That's not the way we have chosen to do it. Instead, we are storing the state transitions. So, for example, a shopping cart, the cart, you add some items to it, you add some more items to it, you add shipping information, and all these transitions are captured, and it's the transitions that are stored. And from these events, you can replay them and reconstruct the state. And the events themselves, the transitions that you store, they are of course immutable, so you can't change them. You can't undo something. So when it has happened, it has happened. Instead, if you want to kind of modify the shopping cart, you add another event. And that also applies to when you remove things. So removal is another event. In that way, you capture the full history of what actually was. And this is often referred to as event sourcing. And those transitions that we store, they are typically named domain events. The domain events, they represent things that has actually happened, something that is completed that can't be undone, can be known as facts. And the naming of those domain events are typically in the past tense, something that has happened. So an invoice has been sent. And also if you're into domain-driven design and think that naming is important in your domain model, those domain events are part of your domain model and should be explicitly modeled there. And that's something that Greg Young recognized quite some time ago. This has also been acknowledged by Eric Evans, the author of Regional Domain-Driven Design book, that this is an essential building block that needs to be added to the building blocks in domain-driven design. And it wasn't there from the beginning. So what's the benefit of storing this state transition compared to storing the state itself? There's several things that you get from this. Of course, you get the auditing and tracing, so you actually see what was going on and each step of the history. That can be important for the business to be able to see what actually was going on, especially if there's some kind of doubt of how did we end up in this state. For example, think about a bank account. It would be rather scary if only the balance was stored all the time and not the actual transactions that made up that balance. So that's the transaction history of a bank account is a typical example of event sourcing. Another thing that is very important for the business side is that you can provide new features and also apply new features to the history, to the data that you have captured previously. Typically, when you build a system, you can't release everything at once. You start with something, and then the business decides that it needs to add some more features. And since you can replay the data, the events, with those new features, you can actually create important information from the history. Scalability and performance perspective, this is very good because since we're storing the events in a kind of a stream, you only append new events, you never remove them or modify them. So it's an append-only log, and that is known to be very performant, and you can have very high throughput of that. Also, the immutability aspect is important because that makes it easy to replicate these events to other servers. For example, you can have query sides that reconstruct some state from these event streams, and you can scale the read sides by having multiple read sides on different machines. From a testability point of view, it's also nice because you perhaps know that the sequence of events that a scenario should end up with. Now you can try the input and then compare the resulting events with your expected events. And it becomes very, very explicit and clear what was going on. And that is especially important in production scenarios when something bad goes on in production. You can take the events and move them to development or test environment and reproduce the scenarios. That's something that can be immensely useful. And also, since you don't store a very advanced structure, it's just those events in an ordered log, there's no need for an object relational mapping tool. And that also makes it possible to use data stores that are optimized for this append-only mode. That means you don't need to have a SQL database. You can use some kind of NoSQL database or something that is really optimized for this use case. And also, since we in Akka use actors, we are already event-based. So this is a familiar concept for us. And therefore, it's also a very nice fit with actors. So this is what we have chosen to use for storing the state of actors. But said that, it doesn't mean that it should be applied everywhere. Of course not. For example, queries is not very well supported by this model. If you have advanced ad hoc queries, then you better use some kind of relational database or something that supports the queries in a better way. But for the actor state, it's a nice first storage mechanism. There's actually two ways of doing this. They're very similar, but a little bit different. And let's take a look at those two ways. And they're called command sourcing and event sourcing. And both these ways are supported by Akka Persistence. So you can pick and choose and use the one that is most suitable for what you need to do. First of all, command sourcing, that is storing the incoming events or messages before you process them. So it acts like a write-ahead log. That means that the incoming commands, the messages, are the things that you store. So you get a kind of tight coupling of the API of the actor and what you actually store. That is both good and bad. It's good in the sense that it's very straightforward. It's bad perhaps from an evolutionary standpoint, since the API is tightly coupled to what you store. On the event source side, you don't store the incoming commands. Instead, you derive events from them. It can, for example, be in a trading application, you have an order that comes in, place order, and from that you generate events like order placed and perhaps also a trade if there's a matching order on the other side. So it doesn't have to be one-to-one mapping from the commands to the events. You can derive events from them. When you use command sourcing, you always do the same behavior when you replay those events as when you have normal operation. So everything is done in the same way. That's also rather straightforward, but it can be a bit problematic, especially if you have external interactions. For example, charging a credit card that should probably be done with care during the recovery. So therefore, you must think about that, and the receivers of the external side effects, like sending out messages to others, they must take care of this, either be idempotent or you must filter out the duplicates somehow. And Akka Persistence have some support for that, which I will show you later. In event sorting, you only apply the state changing, the internal state changing behavior during recovery. So you have different, you do it differently in the normal operation to what you do in recovery mode. Regarding validation, with command sourcing, since you have already persist the command when it arrives, it's not that straightforward to reject commands. I mean, you can just ignore it, but it will still be stored and it will be replayed. One way around that would, of course, be to place some kind of actor in front that does the input validation. But what can't be done there is if the validation is also acting on the current state. And that is different with event sorting. Then you can do validation before you persist the events, and you can just make them fail, make the commands fail and don't do anything. On the other hand, once you have created the event and persisted it, that part can't fail when you use event sourcing, since that's the part that you do in the replay mode. Also, a bit different when you do changes to the logic. With command sourcing, if you do a change, that logic will be applied again when you do the recovery, and that means that you might end up in a different state than it was from the beginning. Perhaps that's exactly what you want, and then it's a good thing. But it can be also a bit tricky. For example, if you have external queries like asking for exchange rate, and that affects the end result. That is something that must be taken care of, because you probably don't want to ask for the exchange rate of the date of when you do the recovery, but when the command was actually performed. So that is also the interaction part that can be a bit tricky when you use command sourcing. And also the naming is different, and that's something that's important that you should respect when you do command sourcing versus event sourcing. You should try to use different naming. Command sourcing, it's represent an intent, something you ask for, a request to do something. It's in naming. While in event sourcing, it's in the past tense, something that has complete. Yeah, what about storing things? It's important to think about the transaction boundaries, the consistency boundaries. And with actors, we have a natural consistency boundary, and that is the actor itself. So that's the part that you can maintain invariance within. Across actors, you can't have this consistency, since you only talk between actors with messages. In domain-driven design, this corresponds very closely to the aggregate building block. So if you're into that, you will recognize this as the aggregate. And there's no distributed transactions in this model. We suggest to accept eventually consistent, and if something ends up in an inconsistent state between parts that should in the end be consistent, you need to do compensation actions instead. And all those compensating actions are also recorded, of course, in the event streams, so you can go back and see what actually was going on. You can read more about distributed transactions and why not to use them in this excellent paper, Life Beyond Distributed Transactions by Pat Helland. That's a really good paper that I can recommend. So let's continue with more hands-on how to use Akka Persistence and the different building blocks that we will look at. So it's the processor that is the way to do command sourcing, and then the corresponding event sourced processor to do event sourcing. And then we have the view that is a way to replicate the event stream from a processor to another actor, which is a view which can resist on another machine typically. And then to do the more reliable communication between actors, we have the channels, the persistent channel and the channel. I'll talk about the differences between those two later. And things are stored in the journals. I will mention a few words about that, and also how to use this in a clustered environment. So let's start with the processor. This is the minimal processor that you can write. So it's a class that extends processor, and you need to implement the receive function. And that looks very much mailbox. Well, it has support for stash, and that gives a special mailbox, but apart from it's not any special mailbox, and that means that when you send a message to it, a persistent message to it, it's not stored immediately. It's stored before it is received. So once you read in that, then it has been stored. But while it's in the mailbox or in transfer to the journal, then it's not stored. And also it doesn't have any special flow controls. It works in the same way as other actors. If you send too much to it, things will queue up, and the mailbox will be holding all those queued up messages. That can be especially important for processor persistent actors, because the storage part of this will of course have a price. So you have much lower throughput of a persistent actor like this than a normal actor. So you must build in some kind of flow control if you are sending a lot of things to it. And by flow control, I typically mean that you have some kind of acknowledgement, or you actually are things. So let's look at it more involved example. So let's say we build an invoice service. The first thing we want to do is to be able to create invoices, and an invoice has an ID. So when we receive a persistent create invoice message, we just update the state, the internal state. In this case, it's just an ordinary map. So that's very straightforward, nothing strange there, I hope. Let's add some more features to this. For example, we can add items to the invoice. So we can add invoice item message to it, also persistent message. And we update the state, very similar. Or we can send just an ordinary message, which is not persistent. We can reply to the sender exactly as normal. Or we can instruct this invoice service to send the invoice to printing servers. That will become a little bit more complicated. So we'll go into that a little bit later. The reason why it will be more complicated is, of course, the recovery part. When this processor is restarted or started up in a new actor system, then those persistent messages will be replayed. That also means that everything we do here will be done again. That's fine when we just updating the internal state, but think about the printing service. So for reference, here's some more code for the messages and the state, in case you look into this later. One thing that is important to know, that is the identifier that is used for storing all those messages is important. So each processor has an identifier. The default identifier, if you don't specify anything else, that will be the path of the actor. So the full name, including the names of the parents, except for the actor system name and the host name and port. So it's only the logical path. So that's typically a good name because it's unique within an actor system. What you should not use if you use the default identifier is to create actors without names, because then they will have those $A, $B names, which are rather arbitrary and will probably not match up the next time you start the system. Another way which is good is to override the process ID definition and define something else. That is your known stable identifier for this processor. So that's a typical gotcha that you need to know. As I mentioned, when you restart or start up a fresh processor, we'll read the events that have been stored from the journal and replay them, and you do exactly the same thing again. This is automatic, so you don't need to do anything special to have this behavior. That is the default, and you can't do anything else, so you can't opt out from it. What you can do is that you can override it and send a special message which is called recover to the actor, and then it will start this. this is exactly what is done by default. But if you override the pre-start or the post-restart methods, then you can override this recover message, and that can be used if you only want to replay up to a certain point in history. So if you want to look how it was back in time, then you can override this behavior. During this recovery phase, all other messages that are sent to the processor are stashed, so they are not received recovery message. Instead, that they are placed in a buffer, and when recovery is then and be processed, means that you can start using the processor immediately from the outside without worrying about what is going on in the recovery phase. Failure happens when an exception works in a similar or the same way as ordinary actors. That is, the supervisor, the parent actor, will take care of the exception and decide what to do. So if you want something else than default behavior, which is a restart, then you implement that in the supervisor. That can be important to know then that the commands, since they are persisted before they are received, they will also be replayed. So if a specific command generates an exception, it will probably generate the same exception next time. Therefore, you can consider to delete the command. Yeah, I said that messages are never deleted, but for this special case, you can mark a message as deleted, and it will not be processed again during recovery. If storage of the messages fail, then there is a special message that is sent, that is persistence failure. So and that will be stopped by throwing an field exception to the supervisor and the defense to want something else, you can override by handling this persistent failure. Yeah, let's get the print service. You need to think what this during replay. And for that, Akka Persistence provides one thing that is called channel. And it can deduplicate outgoing messages from a processor. So in the processor in a channel, it's a special that you send the message, and you send special deliver messages, and that means that the recipient will receive a special confirm persistent message, and it's up to the receiver to say receive this and confirm it. And once the application level confirm is done, then the channel will store that, and the next time the process sends the same thing, it will deduplicate, not send it. So channel can be used to deduplicate out messages. They also serve role. We'll talk about that. That is for the resend and reliable messaging. The corresponding event source processor doesn't store in commands, and you can think of the process those commands in 4 steps. So first, you typically validate the command, and then you create a domain event from it, and you explicitly persist it by calling a method called persist, and then you update the internal state, and you do that by, we say you apply the event, the domain event, and then you can do external side effects. External side effects that can be like messages or do other call to another service. That can of course be done in between all those other steps. So depending on your use case, you might want to do that before the persist event. But that means that you could end up with doing the side effect before actually have a successful storage of it. And sometimes that's what you want, sometimes not. And when you only do the step where you update the internal state, that is by applying the events that are stored. So then you don't do any external side effects. And that's the big difference from command sourcing, that you have different behavior during the replay versus the normal operation. So let's look at how this looks like. Let's say we want to do a little blog post actor that is event sourced. You need to implement two methods, receive command and receive recover. Receive command is for normal operation when you receive commands from the recover is invoked when that recreated during restart or a fresh start. So let's say we want to add a post. We can receive a command, add post. That's just an order message, nothing special at all with that one. And from that one, you derive another event, a domain event, which we call post added, and you call persist. That instructs it to store it. And then in the block here, which is like a callback, which is called when the persist completed, update 8 of this act. This is a callback, a future callback. It's actually run after event loop. So it's referred to state of the actor inside this block. My recommendation is to capture the state as an immutable class and have a method like updated that takes those domain events and creates a new copy of the state. So you have an immutable thing that is updated based on the incoming or the events that are applied. Here's some more features added to it. It works in the same way. I will not go through everything of it, but you can look back to this later. You can add validation to it. You can update the state in different ways. And well, one thing I should mention is receive recover. Then you receive those events, and then you only apply those to the state. That's the beauty of this updated copy method in the state. So we do the same thing when we actually apply the events to the state. And yeah, I've mentioned several times that during recovery, things are replayed, see the same messages again, or same events in the event-sourced case. For long-lived processor, that means that the event stream can be very, very big. You can have a lot of events, and it can take a long time to recover the state. And therefore, there's support for snapshots. So you can store the state, the current state, in some kind of serialized form. So when you recover, you can start out with a snapshot, and thereafter receive the events after that. The way to do that is called save snapshot and pass in something that can be serialized. Then you get back a message telling if it was successful or failure. Everything is asynchronous, non-block course. And during the recovery, you receive a snapshot offer as the first thing, and thereafter you receive the persistent messages that are after the snapshot. So the views is a way to replicate the event stream to another. And the way it works is that it reads from the journal, the same journal as the processor has used for storing, and it periodically reads the event stream and replaces the messages or the events that it hasn't seen before. Typically used as side of EQR, if you're familiar with that. The is automatically read from the journal periodically and update view with that. You can behave and instead read it with an update message. You can configure it to replay more than, for example, 1,000 messages at a time, and also can have can speed up recovery of the view itself. But apart from that, the view is read-only. Of course, it can generate some other state or representation and store that with some other actor. This is how a view looks like. It's the thing you need to define is the identifier, the processor that it should use to read from, and you can define things like the update interval, and you will receive the persistent messages that comes from the processor unit. So we have covered the building blocks for the processor event sourced and view. We have mentioned a bit about channels. Persistent channel is the next thing that we'll look into. So that is for doing this a little bit more reliable messaging between actors. The default delivery mode is at most once in Akka, so a message might be dropped, and then it's dropped. So if you have something important from one actor to another, and you want it to be delivered, several things can happen on the way. Either it's just dropped because the network flake, or the destination is unavailable, might have crashed. So there's no way for the sender to automatically know that. And the way to solve it is to have some kind of acknowledgement back. You send a message back to the sender, say, I received it, everything good. But what about if that is also lost? Well, then you typically retry. So you send the message again, and eventually you will end up with delivery and acknowledgement. This mode is called at least once delivery. At least once means that it can be delivered several times, especially if, well, that will happen if the acknowledgement back is lost. Then you will retry and you will receive the message again in the destination. So it's a completely different semantics from the other normal semantics in Akka. And this is provided by Akka Persistence in what we call a channel and persistent channel. They do exactly what I described. They redeliver until they get a confirmation. And this confirmation is on application level. So it must be the receiver that acknowledges. It has different semantics, as I mentioned. So it can receive duplicates. The order can reach of the messages. So that will happen if the message is not arrived, you retry, or if the first is not heard and the second move is heard and you retry one, and then you ended up in different order. Second before first. It's different, and therefore in the channels you path as a factor. So that's the reason why when you use a channel, a path, and a path, I mean string representation of the name of the actor. So there's two different types of channels. One is called just channel, and that is the purpose of that one is to use it together with a processor, because if you restart a processor, it will do the same things again and will send out the messages through the channel again, and then the channel can deduplicate. The purpose of the persistent channel is the standalone usage, the difference there is that it's actually storing the messages before it's starting to deliver them. So that's useful if you have an ordinary actor and want to use the feature standalone. See that I am running out of time compared to the plan. We'll go through the rest of the things a bit quickly. Might take 5 minutes. You have to interrupt me, James, if that's not okay. Yeah, you can look into the code examples later on to see how you can use the channels and the persistent channels. This example is it can be interesting because that when you have some endpoint, a system boundary, you receive something from the outside, and the first thing you want to do is to store that incoming request. And once you know that it has been stored, then you want to reply back to the sender and say, yeah, I will take care of this. So a persistent can be used for that if hand use case. Serialization of messages, of the persistent messages, are very important, both from performance perspective, but also when you start thinking about the application life cycle. So when you evolve the application, the representation will typically change. That's something mechanism. And since we are using the ordinary Akka serialization, which is completely pluggable, you can create your own serialization. And I personally think it's a good thing to use something, a totally different representation from your domain classes. For example, defining the messages in protobuf and then have a conversion layer in this serialization so that you can map things from the different representations. And that way you can also handle the versioning. And by all means, don't use the default Java serialization. Both slow, and it will definitely make it very difficult to handle the lifecycle. So things are stored in a journal, and by default, what is shipped with Akka is a local level DB journal. So that can be used on a single node, and it stores things in the file system. The journal implementations are completely pluggable, so you can add your own journal or use the ones that are already built by the community. There's a list on this community page of Akka where you can see the current journal implementations. Some of those are probably not production ready yet. Some of them are probably in better shape. For example, the Cassandra one is developed by Martin Kresser himself, so that's probably in pretty good shape. A few words about how to use this in a cluster as well. From a cluster, you need to be able to access the data in the journal from these different nodes, and therefore you need a distributed journal, like the Cassandra MongoDB journal that I showed in the last slide. For testing, there is a variation of this level DB journal that is shipped with Akka. It's a shared level DB, so you can use it remotely, but that's only for testing because it becomes a single point of failure. What's important is for one processor or event source processor, you can only have one actor that is writing to that specific stream. So in a cluster, you must make sure that you are only running one instance of that actor. And for that, we have two utilities that can be used. They are part of the Akka Contrib module. It's the cluster singleton and the cluster sharding. First, the cluster singleton that works so you can define actors that are started on the oldest member of the cluster. So if you have a few actors, you can define them as singletons, and they can be persistent actors, processor or event source processors. The drawback with this is that all of them will be running on the same node, the oldest one. But you still must have other spare nodes for failover. That can be improved a little bit by using cluster roles. Then you can say that a few of those actors run on one role and a few others on another one. But still, you must have those spare failover nodes. So this is perfectly fine if you just have a few of the few processes. But if you have many or want a more dynamic way of doing it, you should look into the cluster sharding, because that makes it possible to spread all those actors over all nodes in the cluster. And the way it works, just quickly, is when you send a message, you send it to an identifier, and the identifier corresponds to the actor that is the recipient. So as a sender, you don't care, or you don't know where the destination is running. That is taken care of by the cluster sharding. So you don't send the message directly to the actor, you send it through this cluster sharding regions. So the regions are started on each node, and you send the message there. And when a region initially receives an ID that it doesn't know where to route, it asks a central coordinator. So you must have one point that decides where to allocate this specific actor. And it decides where to do it, and in this case it says on node 2. And then it can route the message there, and the same thing happens there the very first time. So it has to ask as well, and then finally it knows, yeah, I'm responsible, and can create the actor, and the message gets routed to the destination. The next time, everything is set up because those locations are cached, so the message can just be routed through without the coordinator. And this also, of course, works fine with if something crashes, the coordinator takes care of allocating the actors on another region, another node, and so the cluster, it will rebalance things. And in reality, it's not working on the actor level, on the individual entities. It's actually a group of entities, which is called a shard. And that's for scalability reasons, so you can have very many of those actors. There's some sample code as well. I'll just quickly skip those. And let's go on to the questions section. Here's some references to links that you can look into later. I especially recommend that you try out the type-safe activator templates. There are 3 of them. The samples from the documentation are provided as type-safe activator, so you can run them. And also the cluster sharding is a separate template. So try them out. If you have some questions later on, you can use the main list. Also, a good thing is, as participant of this webinar, you will have a subset of the Akka in Action book for free. You will also have a discount on the book later on. Yeah, that's my slides, and sorry for the rush, but any questions now?
That was great. Yeah, thanks, Patrik. So there's been some great questions that have come in. We have a few minutes left. So before we go into those, wanted to make sure you know that we are going to be posting the recording of this, and we'll email everyone that was registered a link to that recording, and that'll be up in the next day or so. So one question that came up was, are you going to post your slides somewhere online so that people can go review those as well as the recording?
Yeah, definitely. Actually, I have already posted them on SlideShare. I can tweet the link.
Great, that's perfect. Then I think you mentioned the Akka user list is a great place to post follow-up questions. So unfortunately, we don't have a whole lot of time left, but if you have unanswered questions, ask those on the Akka user Google group. Then a couple of people asked about this feature being experimental and wondering when they'll be able to use it in a production system, when it will be out of experimental mode.
Oh, that's a good question. I probably perhaps forgot to mention that experimental doesn't mean that it's not tested and has good quality. It's definitely ready for production right now. It's just a way for us to be able to evolve it in a little bit more free way than otherwise.
So the APIs could change, but it's considered pretty stable in its implementation.
Yeah, that's right.
Great. And there was, oh, can you flip back to the slide on the resources?
Yeah.
For people. Great. And there's a question about the Akka in Action ebook. How can they get that snippet? Will we be emailing that out with the recording link, or do you know how we're distributing that?
That's correct. It will be part of the email that is sent out.
Awesome. Great. Let's see. There was, we have time for maybe couple questions. One is, can I have a separate journal and snapshot store? So for example, can I use MongoDB for the journal and LevelDB for the snapshots?
Yeah, that's right. They are separate, so you can use different implementations for those.
Great. Let's see. There's been a number of questions. I'm sorry we won't have time to get to all of the questions here. Let's see. We'll pick one last good one. Is there only a one-to-one relationship possible between a processor and a view, or can you have multiple views on top of a processor?
You can have several views that are connected to the same processor. So that's right. But what you can't connect one view to several processors. So it's a one-to-many mapping.
Great. Great, that makes sense. All right, well, unfortunately we're out of time, but if you didn't get your questions answered, then really the best place is the Akka user list on Google Groups for that, and we'll be in touch about the recording.